Chapter 11 in this book is all about power series solutions, and I can tell by the sound of your voice that you are excited about this. I know the power series are usually anxiety-causing things, so why don't we do some review just to make sure we're all on the same page and get rid of some of that anxiety. So I wrote a bunch of words here and you should read them, but let's just kind of review the basics. A power series is of the form, the sum from n equals 0 to infinity of cn x to the n. I go back and forth between using c's and a's in this. I don't really know why. This just stands for, when you plug in 0, you get c0 times x to the 0, which is just, 1. And then plug in n is 1, you get c1 x to the first, plug in n is 2, c2 x squared plus, and on and on and on. X is a variable, and the cn's are called the coefficients, okay? And we're going to have to do a bunch of stuff with these, which are arithmetic type of manipulations, but let's just start with the peeling off a term, so to speak. If I start from 0 to infinity, this stands for that series. What if I wanted to just start right here? Well, all I'd have to do is just say n equals 1 to infinity, and I sort of be peeling off the 0th term, and the rest of it starts at n equals 1, okay? So not a lot going on there. That is totally okay. Let's go through some more definitions here. A power series does not have to be centered at 0. It can be centered at some other point a. Okay, you can say a power series in x minus a, and all we're doing is swapping out just the x for x minus a. All right, a word about convergence. We all know that series don't need to converge, but what can we say about this? A power series converges for x equals a, provided, when you plug in a, this limit exists, okay? Now, this limit is a limit of partial sums. These are the partial sums going from 0 to some fixed number, and then you let that number go to infinity. Okay, so this limit here is a limit of partial sums. If that limit exists, then the series converges. If it converges on an interval I, we say it converges on interval I if it converges for every x in that interval. Okay. We have a very similar statement when this thing is shifted over. Okay, so whether you're dealing with one like this or one like this, you can say all the same things. You're just kind of substituting in x minus a. Okay. Next, speaking of convergence, so this power series, there are only 3 possibilities. It can converge only when x is 0, and we should say that when x is 0, it always converges because all of these go away and you're just left with the first term. Okay, so it will always converge at least that point, or x equals a in the case of this one. So it could converge just for that one. It could converge for all x, so for all of them it can converge, or for some interval. Okay, then the intervals will be centered at the point 0, and plus or minus some number called the radius. Now, it may or may not converge at that endpoint, so there are 4 different ways that this could look. It could look from minus r to r. It could go from minus r to r. It could go from minus r to r. Or it could look from minus r to r, depending on what happens at the endpoints. It's very easy for them to either converge or diverge. And in Calc 2, what often happened was one of these things ended up sort of being the harmonic series and the other one didn't. That's kind of how it worked. Okay, and here's the picture. Okay, here is the interval of convergence. This thing is the radius of convergence. Okay, the endpoints may or may not converge, and it diverges outside. Okay, that's what all of these look like. Okay, so how do we determine what that radius of convergence is? Well, one of the best ways was to use the ratio test, and here's how it goes. Let this thing be a series, and let the limit as n goes to infinity of the ratio of consecutive terms, a sub n plus 1 divided by a sub n. That limit is L. If L is less than 1, then it is absolutely convergent. If L is more than 1, then it is divergent. And if L is equal to 1, then the ratio test is inconclusive. Okay, so let's use that on a series right here. So example 277, determine the radius of convergence for the following power series. That one right there. So let's use the ratio test. So we will take the limit as n goes to infinity of, okay, I have to write a bunch of stuff down, okay? So let's kind of zoom in here. Negative 3 to the n plus 1 divided by, and we'll put x minus 2 to the n plus 1. N plus 1. 8 to the n plus 1 is n plus 2. Okay, we can work that out. Negative 3 to the n. X minus 2 to the n. N. 8 to the n plus 1. Now, it looks very complicated here, but this simplifies very nicely. Limit n goes to infinity of what? Okay. Negative 3 to the n plus 1. Oops. N plus 1. 8 to the n plus 2. Times, okay, x minus 2 to the n plus 1. And then you flip the bottom and multiply. So then I get n here, 8 to the n, negative 3 to the n, 3, x minus 2 to the n. Okay, a couple things all at once here. That's a plus 1. What am I left with? So those cancel with those, and let's use a different color here. Let's cancel in red. Those cancel with all of those. Negative 3 on top. I have an n over an n plus 1. Those don't cancel. I have 8 to the n plus 1 cancels with all but one of those. There's an 8. And then what happens here? So I have n plus 1 on top and n of them on bottom. So I have x minus 2. And that's the limit as n goes to infinity. Now I want to pull out all of the stuff that doesn't have n's in it. Okay, so that's going to be positive 3/8, absolute x minus 2, right? There's only one of them, and it's got these absolute value bars on it. And then this is times the limit as n goes to infinity of n over n plus 1. And now I've got a limit that I can do. This limit is 1. So that whole thing is 3/8 x minus 2 times 1. Now the ratio test says that this will converge absolutely whenever that limit is less than 1. So what do I need to do? I just need to take 3/8 x minus 2 and set it to less than 1, not L, 1. So then x minus 2 is less than 8/3. And I essentially have my radius at this point right here. So the question was only asking me for the radius. Determine the radius of convergence. And this is the distance between x and 2. And so this just means that it's centered at 2, and as long as x is within 8/3 from 2, then it will converge. So the radius of convergence is 8/3. All right. Now, if I wanted to find the interval of convergence, I would need to check it, okay? So this essentially converges for 2 plus 8/3 and 2 minus 8/3. And what I would need to do is check each of these points separately. They may or may not be included. Okay, I don't know. So this isn't the interval. This is just the potential interval there, okay? I would need to check the endpoints. So, but I got the radius, and that's all the question asked me for. Very good. It's been a while since we did one of those. Those are fun. Okay. Suppose that we have a power series function that looks like this. So this is just a series here, right? The power series function, but except we're calling it a function now instead of just the series. And really, this is not doing anything different. We're just saying that, you know, for this value of x, it's going to plug in right there. So since it's a function now, how do I take derivatives and integrals? And the answer is, well, this is just the power rule here, right? This is sort of a infinitely long polynomial. And so I can take the derivative term by term. And I included all the details here, but that's essentially what happens is, bring the power down, subtract 1 from the power, and you get this thing. I take the derivative term by term. Note that you start at n equals 1. Why? Well, because the n equals 0 term was just a constant, and so the derivative of that one was 0. Okay, so starts at n equals 1. The antiderivative is the exact same thing. You increase the power by 1, divide by the new power, and then add the c. And we write the c at the front just so we don't sort of get confused that it's inside the sum. And this is the constant. This is the sort of n equals 0 term, because n equals 0 right here actually is a power of x, right? So that actually is x minus c to the 1. All right, so all of these have x's in them. Here is the first one that does not. Okay? So let's try one for fun. Let's say f of x is x to the n over n factorial. So f prime of x is going to be n equals 1 to infinity of n x to the n minus 1 divided by n factorial. And this is kind of a fun one, because n equals 1 to infinity, x to the n minus 1 over, now n factorial is n times n minus 1 times n minus 2, and so on. So if that one cancels with that one, this is n minus 1 factorial. Now, we're going to do some more of this in the pages that follow, but I can actually shift the index here, okay? So if you want to see this sort of worked out, you can say that, let's say, I is equal to n minus 1, right? So this is the power right there. And so it's going to be x to the I over I factorial. Now, as n goes to infinity, so does I. That's good. And then where does I start, right? When n is 1, I is equal to 1 minus 1, which is 0. So I starts at 0. Now, with that index shift, I can actually see that I get back to f again with just a different variable. So in this case, I found the derivative, and it turns out to be f of x again. And as we possibly remember, that is the Maclaurin series for e to the x. All right? The next ones are going to be a bit more of this, but I think this is a good place to take a pause, and I will see you in the next one.